All right, this is the second video on the fundamental theorem of calculus in AP Calculus. This is section 5.4 in your textbook. So we're going to begin with discussing how to find total area analytically. So we've already kind of discussed in this unit the fact that there's a difference between area and integrals. Integrals can be negative. They are directional in terms of being below the x-axis, or if you're integrating in a leftward direction instead of a rightward direction, then it's possible that your integral values could be negative. Area, on the other hand, always has to be positive. So if you get an example like this one where it says find the area of the region between the curve y equals x cosine of 2x and the x-axis over the interval from -3 to +3, it's very important that you understand they're asking you to find the area. So if we look at the regular graph of x cosine 2x, that's the first graph that we see here. Notice that part of it is above the x-axis, part of it is below the x-axis. And in fact, if you look at that, if we took all the pieces above the x-axis, they match up perfectly with a corresponding piece below the x-axis. So the actual integral value for this from -3 to +3 would be equal to 0. However, to find the area under the curve, we have to find the area of each of those 6 little sections individually and add them all together. So that would require figuring out every single one of these x-intercepts here and doing an individual integral for each section of that x-axis. So that would require 6 different integrals. The 3 pieces that are below the x-axis, when I find them individually, I would then need to make them positive. So we think about with a calculator how we could go about that, because obviously with this function x cosine 2x, we would need to use a calculator probably to solve, to find where those zeros are. Well, not necessarily. So we could take x cosine 2x, set it equal to 0, which would mean if we separate the factors, so there's 1, which I could have told you was right here, but now we have 4 more we have to find. So that comes from cosine 2x equals 0. To get rid of the cosine, we would do inverse cosine of 0. Well, where on the unit circle does cosine equal 0? Well, that is at pi over 2 and at 3 pi over 2. But we're also going in the negative x direction, so that means we could also use negative pi over 2 and negative 3 pi over 2. Now, those are what 2x is equal to, so that means that x would equal pi over 4, 3 pi over 4, negative pi over 4, and negative 3 pi over 4. So here's negative 3 pi over 4, negative pi over 4, pi over 4, and 3 pi over 4. So for the sake of room, I'm going to erase all that where I set it equal to 0. So if you need to pause the video real quick so that you can write that work down, I would suggest you do that. All right, so that means that I would then have to integrate from -3, oops, that's supposed to be negative, okay, to -3 pi over 4, x cosine 2x dx. But notice that's below the x-axis, so I would need to make it the opposite sign, so I'm going to stick a negative out in front. And then we would integrate from -3 pi over 4 to negative pi over 4, x cosine 2x dx. That one's above the x-axis, so we can keep it positive. The next piece would be below the x-axis, so we would want to do the negative of him from negative pi over 4 to 0 for x cosine 2x dx. And then from 0 to pi over 4 is already above the x-axis. Pi over 4 to 3 pi over 4 is going to be negative, so we'll need to put a negative sign in front of it. And then lastly, from 3 pi over 4 to 3. So again, that would require finding 6 integrals and integrating them to get that final answer. But instead, what we could do is we could go to our calculator. And we could go to Math 9. And if I wanted to go straight from -3 to +3, I could not integrate x cosine 2x. I would need to integrate the positive version of x cosine 2x. So what we could actually do is we could go to Math, get the absolute value, and inside the absolute value we could put x cosine 2x. Make sure that you're in radians as well. So now by integrating the absolute value of that function, that takes the function, puts it above the x-axis for everything, and then we can go straight from -3 to +3 without stopping. But notice the absolute value has to go around the function, not around the integral. So if we do that, it takes your calculator a minute because it does it the way that we initially did it, which is with a whole bunch of little tiny rectangles. And so when it is done thinking, we get 5.425. So the total area is 5.425, which is also the answer we would have gotten if we had done these 6 individual integrals and pieced them together, making the negative ones the opposite sign when we need to. So that's how you find total area under a curve. The next thing we're going to look at is finding total area numerically. So that's the Math 9 concept. But we do Math 9 of the absolute value of the function. So that's essentially what I just showed you there on the calculator. So what if, though, we're just given some information here? So this says the graph of a continuous function with domain from 0 to 8, it's a closed interval, is shown. Let h be the function defined by the integral from 1 to x of this function. So this is the graph of f. Notice that to integrate, h is going to start at a value of 1. That is important. So we've got 5 different questions here that we're going to answer based on this given graph of f. So A wants us to find h of 1. So if I go straight to the way that h of x is written and replace all my x's with 1s, that means that h of 1 would be equal to the integral from 1 to 1 of f of t dt. Well, I don't even have to look at the graph. Notice that the beginning and the ending of my integral intervals are the same. So I have 0 width at all to the area that I'm finding. So that's always going to be a 0. Hopefully you remember that from our properties of integrals from previously. Then we have, is h of 0 positive or negative? Well, again, if we think about substitution, h of 0 is going to be the integral from 1 to 0 of f of t dt. So if I go from 1 backwards to 0, that's going to be a -1 in the x direction. And I don't know exactly what all these heights are, but they're all positive. So I would have positive y values times a negative change in x. So that is going to be negative. And your reasoning, because it says justify your answer, could be because the change in x is negative while all the y values in the interval are positive. All right, then we have C. Find the value of x for which h of x is a maximum. So h of x is essentially the accumulation of area starting at x equals 1, because they told me to, and going to wherever. So a maximum would be where I have accumulated the most positive area I possibly can. Well, obviously going backwards, we've already figured out that that's going to be a negative amount of area. So if we go to the right, initially I'm accumulating positive area. And I accumulate positive area all the way until I get to there. At that point, I start accumulating negative area. So that's going to do nothing but deplete my overall area value at that point. So my maximum positive area is accumulated here at this x-intercept, which it looks like happens at x equals 4. Now, they didn't ask me to justify, but your justification could be because the integral from 1 to 4 of f of t dt is the most positive area accumulated. All right, then D asks the same question. I'll scroll down to it in a minute, but I want to be able to look at the graph. D says find the value of x for which h of x is a minimum. So if you use where I've shaded here, when we start at 1 and then we get to 4, we're at our maximum positive amount. Then we start subtracting negative area from it. That green shaded area takes up more space than the red shaded area does. It's just a greater amount. So by the time I get all the way to the end here, I've accumulated way more negative area than positive area. So that would mean that the minimum possible value accumulated would happen at x equals 8. All right, and then E, find the x-coordinates of all points of inflection of the graph of h of x. So points of inflection, if we think back to the last graphs unit, that's going to be where the second derivative changes from positive to negative or negative to positive. So changes in sign of the second derivative. Well, if h is the original function, f is the first derivative, so therefore f prime would be the second derivative. So where would the derivative of this graph that I'm looking at, where would it change signs? Well, since it's the derivative of the graph that I'm looking at, it's going to change signs wherever the slopes of this graph change between positive and negative. So at x equals 1, we go from a decreasing graph to an increasing graph. So from negative slopes to positive slopes. Then at x equals 3, we go from positive slopes to negative slopes. We continue to have those negative slopes until we get to 6, and then we have positive slopes again. So those places where the changes occur are at 1, 3, and 6, which would mean that's where the second derivative changes between positive and negative, which would mean that's where the original graph, h of x, has points of inflection. So that's kind of a little bit of everything having to do with area under a curve and a little bit of the fundamental theorem of calculus.